Hi. Hello everyone. Welcome to information sharing session on failure analysis. Forging and extrusion process defects. In previous session, we discussed about casting process defects and primary processing defects like rolling, seam, non-metallic infusions, delamination, and exfoliation. Today, we will discuss about some more primary processing defects related to forging and extrusion process. Forging is a metalworking process that involves shaping metal using localized compressive forces. The metal is heated to a specific temperature, making it more malleable and easier to deform. The shaping is typically done using a hammer or a die. Forging can be done at different temperatures, resulting in different types of forging. Cold forging, forging done at room temperature. Warm forging, forging done at temperatures above room temperature but below the metal's recrystallization temperature. Hot forging, forging done at temperatures above the metal's recrystallization temperature. Forging is a versatile process that can be used to create a wide variety of metal products, from simple shapes like nails and bolts to complex components like gears and engine parts. It is a strong and durable process that can produce high-quality products. Although great care is exercised in producing a sound forging, various types of defects, such as folds and laps, push-through defect, thermal crack, burst, undesirable grain flow, etc., are often encountered. Ultimately, these defects result in failure. We will learn about these defects. Folds and laps, and undesirable defects in forging. Folds and laps are common defects encountered in the forging process, impacting the quality and performance of the finished product. These surface imperfections arise when metal folds back onto itself during forging, leading to internal and external discontinuities. Causes of folds and laps. Improper die design. Dies with inadequate draft angles or sharp corners can trap metal and cause it to fold. Underfilling or incomplete filling of the die cavity can also lead to folds. Insufficient material. Using less material than required for the desired shape can result in incomplete filling and metal folding over itself. Excess lubrication. Excessive lubricant can prevent proper metal flow and trap air pockets, leading to fold formation. Improper forging temperature. Forging at temperatures that are too low or too high can limit metal flow and increase the risk of folds. Uneven pressure distribution. Unequal pressure application during forging can cause localized folds and laps. Consequences of folds and laps. Reduced strength. Folds and laps weaken the forged part by creating internal cracks and discontinuities, impacting its structural integrity and load-bearing capacity. Surface imperfections. Folds and laps appear as visible surface defects, compromising the aesthetics and finish of the forged part. Fatigue crack initiation. The presence of internal folds and laps acts as stress concentrators, increasing the risk of fatigue crack initiation and failure under cyclic loading. Rejection and scrap. Folds and laps often lead to the rejection of forged parts, causing production delays and increased scrap rates. Prevention of folds and laps. Die design optimization. Employing dies with proper draft angles, radii, and accurate cavity design is crucial to ensure smooth metal flow and prevent folds. Correct material usage. Utilizing the appropriate quantity of material for the desired shape ensures complete die filling and eliminates the risk of folds. Optimizing lubrication. Applying the correct amount and type of lubricant allows for smooth metal flow and minimizes air entrapment. Precise temperature control. Maintaining the appropriate forging temperature for the specific material optimizes metal flow and prevents folds. Ensuring uniform pressure distribution. Implementing proper die alignment and forging techniques ensures consistent pressure application throughout the forging process. Simulation and inspection. Utilizing forging simulation software and performing thorough inspections during and after forging helps identify and address potential fold and lap formation early on. By understanding the causes and consequences of folds and laps, and implementing appropriate preventative measures, manufacturers can ensure high-quality forged parts and minimize production losses. Push-through defect, a discontinuity in closed die forgings. Push-through defect, also known as flash breakthrough, is a specific surface imperfection encountered in closed die forging processes. It occurs when the heated metal, under the immense pressure exerted by the forging dies, pushes through the gap between the die halves. This results in a protrusion of material on the surface of the forged part. Causes of push-through defects. Excessive forging force. Applying excessive pressure beyond the material's flow limit can lead to the metal breaking through the die gap, causing a push-through defect. Insufficient die clamping. Improper die clamping or inadequate die closure can create a gap between the die halves, allowing the metal to push through during forging. Die wear and damage. Worn out or damaged dies with increased die gaps can facilitate the formation of push-through defects. Improper lubrication. Insufficient or inappropriate lubrication can lead to increased friction and heat generation, causing the metal to push through die gaps more readily. Incorrect material properties. Forging material with high flow stress or low ductility may be more susceptible to push-through defects under high pressure. Unfavorable die design. Die designs with sharp corners or inadequate radii can create stress concentrations and localized areas of high pressure, increasing the risk of push-through defects. Consequences of push-through defects. Surface imperfections. Push-through defects appear as visible protrusions on the forged part, impacting its dimensional accuracy and surface finish. Material loss. The material pushed through the die gap is lost, increasing production waste and potentially affecting material availability. Secondary processing. Removing push-through defects often requires additional machining or grinding, increasing production time and cost. Reduced strength. In severe cases, push-through defects can create internal cracks or reduce the overall strength of the forged part. Prevention of push-through defects. Precise control of forging force, monitoring and adjusting forging pressure to ensure it stays within the material's flow limit helps prevent push-through. Proper die maintenance. Regularly inspecting and maintaining dies to prevent wear and damage, ensuring tight closure and minimizing die gaps. Adequate lubrication. Applying the appropriate amount and type of lubricant reduces friction and heat generation, minimizing the risk of push-through. Material selection. Choosing materials with lower flow stress and higher ductility can help reduce the occurrence of push-through defects. Optimizing die design. Implementing dies with proper radii, draft angles, and smooth transitions helps ensure smooth material flow and prevents localized pressure buildup. Proper process monitoring. Employing process monitoring techniques, such as load monitoring and temperature monitoring, allows for early detection of potential push-through problems. By implementing these preventative measures, manufacturers can minimize the occurrence of push-through defects and ensure the production of high-quality forged parts with consistent dimensions and surface finishes. Undesirable grain flow, a detrimental defect in forgings. In the forging process, manipulating the metal's grain flow is crucial for achieving desired strength and performance characteristics. However, certain situations can lead to undesirable grain flow, a condition where the grain structure is non-optimal and negatively impacts the forged part's properties. Causes of undesirable grain flow. Improper forging technique. Incorrect forging techniques, such as inadequate die design, improper heating, or non-uniform pressure application, can disrupt the desired grain flow pattern. Uneven metal flow, obstacles in the die cavity, excessive friction, or insufficient lubrication can impede smooth metal flow, leading to distorted grain structures. Excessive forging temperature. Forging at temperatures above the optimal range can lead to grain overgrowth and coarsening, reducing the strength and fatigue resistance of the forged part. Material inhomogeneity. Inhomogeneities in the material composition, such as inclusions or impurities, can disrupt the grain flow and create weaker areas within the forged part. Improper post-forging cooling. Improper cooling after forging can lead to rapid grain growth and non-uniform grain structure, compromising the final properties. Consequences of undesirable grain flow. Reduced strength. Undesirable grain flow can lead to decreased tensile strength, yield strength, and fatigue resistance, making the forged part more susceptible to failure under stress. Anisotropy. Anisotropic grain structure can cause the mechanical properties of the forged part to vary depending on the direction of loading, making it unpredictable and unreliable. Internal cracking. Undesirable grain flow can create stress concentrations within the material, increasing the risk of internal cracking and component failure. Reduced ductility. Improper grain structure can decrease the ductility of the forged part, making it less resistant to deformation and more prone to fracture. Prevention of undesirable grain flow. Optimizing forging parameters. Implementing proper forging techniques, including temperature control, die design, and pressure application, ensures the desired grain flow pattern is achieved. Minimizing friction. Employing proper lubrication and die coatings helps reduce friction and promotes smooth metal flow, minimizing grain distortion. Controlling material composition. Maintaining consistent material composition and minimizing impurities can prevent disruptions in the grain flow pattern. Post-forging heat treatment. Implementing appropriate heat treatment processes after forging can refine the grain structure, improve mechanical properties, and eliminate undesirable grain flow effects. Process monitoring and simulation. Utilizing process monitoring techniques and simulation software allows for real-time analysis of grain flow during forging, enabling adjustments to optimize the process. By meticulously controlling the forging process and implementing preventive measures, manufacturers can minimize the occurrence of undesirable grain flow and ensure the production of high-performance forged parts with reliable mechanical properties. Thermal cracks, a critical defect in forgings. Thermal cracks are a serious defect that can occur during the forging process, significantly impacting the quality and integrity of forged parts. These cracks are caused by thermal stresses induced by rapid temperature changes during heating, forging, and cooling stages. Causes of thermal cracks. Excessive temperature gradients. Rapid heating or cooling of the metal can create significant temperature gradients within the part. This can lead to localized stresses exceeding the material's strength, resulting in cracking. Improper temperature control. Inaccurate temperature control during heating and cooling can lead to inconsistencies in the thermal load on the metal, increasing the risk of cracking. Material properties. Materials with low thermal conductivity or high thermal expansion coefficients are more susceptible to thermal cracking due to their tendency to develop localized hot spots and stresses. Die design. Sharp corners or abrupt changes in geometry in the die can lead to stress concentrations and promote crack initiation. Improper lubrication. Inadequate lubrication can increase friction and heat generation during forging, exacerbating thermal stresses and increasing the risk of cracking. Consequences of thermal cracks. Reduced strength. Thermal cracks significantly reduce the strength and load-bearing capacity of the forged part, making it prone to failure under stress. Fatigue crack initiation. Thermal cracks act as stress concentrators, accelerating the initiation and propagation of fatigue cracks, potentially leading to sudden and catastrophic failure. Material loss. Thermal cracks can lead to significant material loss, impacting production efficiency and increasing manufacturing costs. Rework and scrap. Forged parts with thermal cracks are often unusable and require rework or complete scrapping, resulting in production delays and reduced yield rates. Prevention of thermal cracks. Optimizing temperature control. Implementing precise temperature control during heating, forging, and cooling stages is crucial to minimize thermal gradients and prevent excessive thermal stresses. Preheating and soaking. Preheating the material uniformly before forging and employing soaking times at specific temperatures help reduce thermal gradients and ensure consistent temperature distribution. Material selection. Choosing materials with high thermal conductivity and low thermal expansion coefficients can help minimize the impact of thermal stresses and reduce the risk of cracking. Optimizing die design. Designing dies with smooth transitions, rounded corners, and adequate draft angles helps prevent stress concentrations and promote uniform heat flow. Utilizing proper lubrication. Applying the correct amount and type of lubricant reduces friction and heat generation, mitigating the development of thermal stresses. Post-forging heat treatment. Implementing appropriate heat treatment processes after forging can help relieve residual stresses and improve the overall strength and ductility of the forged part. By implementing these preventive measures and maintaining strict control over the forging process parameters, manufacturers can minimize the occurrence of thermal cracks and ensure the production of high-quality, reliable forged parts. Understanding bursts, a critical defect in forgings. Bursts are a serious internal defect that can occur during the forging process. They manifest as internal or external tears or ruptures in the forged part, causing significant quality concerns and impacting its structural integrity. Causes of bursts. Excessive forging force. Applying excessive pressure beyond the material's flow limit can lead to internal tearing and burst formation. This is particularly prevalent in hot forging processes. Inclusions and voids. Pre-existing inclusions or voids within the starting material can act as stress concentrators and initiate bursts under high forging forces. Improper heating. Insufficient or uneven heating can lead to temperature inconsistencies within the material, causing localized regions to deform differently and potentially leading to burst formation. Die design. Sharp corners, abrupt changes in geometry, or insufficient draft angles in the die can create stress concentrations and promote burst initiation. Material properties. Materials with low ductility or high work hardening rates are more susceptible to bursts due to their limited ability to deform uniformly under high pressures. Types of bursts. Internal bursts. These occur within the body of the forged part and are often difficult to detect without destructive testing. Internal bursts significantly weaken the component and increase the risk of sudden failure. External bursts. These manifest as visible cracks or ruptures on the surface of the forged part. While easier to detect, external bursts still compromise the structural integrity and aesthetics of the component. Consequences of bursts. Reduced strength. Bursts significantly reduce the strength and load-bearing capacity of the forged part, making it more susceptible to failure under stress. Fatigue crack initiation. Bursts act as stress concentrators, accelerating the initiation and propagation of fatigue cracks, potentially leading to sudden and catastrophic failure. Safety hazards. Bursts in critical components can lead to safety hazards and equipment malfunctions, posing potential risks to personnel and surrounding infrastructure. Rework and scrap. Forged parts with bursts are often unusable and require rework or complete scrapping, resulting in production delays and increased costs. Prevention of bursts. Controlling forging force. Implementing precise control over forging pressure and ensuring it stays within the material's flow limit is crucial to prevent bursts. Material selection. Choosing materials with high ductility and low work hardening rates can help minimize the risk of bursts during forging. Careful inspection of starting material. Thoroughly inspecting the starting material for inclusions and voids before forging helps identify potential burst initiation points and address them before processing. Optimizing die design. Designing dies with smooth transitions, rounded corners, and adequate draft angles helps prevent stress concentrations and promote uniform material flow during forging. Temperature control. Implementing precise temperature control throughout the forging process ensures consistent material behavior and minimizes the risk of internal tears due to temperature inconsistencies. Utilizing proper lubrication. Applying the appropriate amount and type of lubricant reduces friction and heat generation, minimizing the development of stresses that could lead to bursts. Post-forging heat treatment. Specific heat treatment processes after forging can help relieve residual stresses and improve the overall strength and ductility of the forged part, further reducing the risk of burst formations. By implementing these preventive measures and maintaining strict control over the forging process parameters, manufacturers can minimize the occurrence of bursts and ensure the production of high-quality, reliable forged parts. Orange peel, a cosmetic defect in forgings. Orange peel, also known as surface roughness, is a common cosmetic defect encountered in forged parts. It manifests as a textured surface resembling the skin of an orange, with small, uneven bumps and depressions. While not affecting the structural integrity of the part, orange peel can impact its aesthetic appearance and marketability. Causes of orange peel. Large grain size. When the starting material has a large grain size, the individual grains deform independently during forging, leading to an uneven surface with visible peaks and valleys, resembling an orange peel. Excessive deformation. Subjecting the metal to excessive deformation, particularly in deep drawing operations, can exceed the material's ability to deform uniformly, resulting in an orange peel appearance. Friction and lubrication. Insufficient or inadequate lubrication during forging can increase friction and hinder smooth metal flow, leading to uneven surface texture and orange peel formation. Die wear and damage. Worn out or damaged dies with uneven surfaces can impart their imperfections onto the forged part, causing an orange peel effect. Improper temperature control. Forging at temperatures outside the optimal range can affect the metal's flow behavior and contribute to uneven surface formation. Consequences of orange peel. Aesthetics. Orange peel can detract from the visual appeal of the forged part, particularly for components requiring smooth and polished surfaces. Paintability. A rough surface can reduce paint adhesion and lead to uneven paint finishes, impacting the overall aesthetics and quality of the finished product. Corrosion resistance. In some cases, an orange peel surface can act as a trap for dust, dirt, and moisture, potentially accelerating corrosion and reducing the lifespan of the forged part. Prevention of orange peel. Material selection. Choosing materials with finer grain sizes can help achieve smoother surfaces and reduce the risk of orange peel formation. Optimizing forging parameters. Controlling the amount of deformation, forging temperature, and lubrication helps ensure uniform metal flow and minimize surface roughness. Die maintenance. Regularly inspecting and maintaining dies to prevent wear and tear is crucial to avoid transferring surface imperfections onto the forged parts. Shot peening. Applying a post-forging process like shot peening can help mask the orange peel effect by creating a more uniform surface texture. Chemical polishing. For specific applications, using chemical polishing techniques can further smooth the surface and eliminate the orange peel appearance. By implementing these preventive measures and carefully controlling the forging process parameters, manufacturers can minimize the occurrence of orange peel and ensure the production of aesthetically pleasing and high-quality forged parts. In next session, we will go through extrusion process defects. Thank you.